Have you ever wondered how we actually know what the structure of a material looks like? I mean, down to the individual atoms? You can't just use a microscope. The atomic world is way, way too small for light to see. So, scientists had to get a little clever. Let's dive into how they pull it off. Right. This is the big hurdle. Seriously, think about it. It's like trying to figure out the texture of a grain of sand by poking it with a beach ball. It just won't work. The waves of visible light are massive compared to atoms, so they just wash right over them without telling us a thing. So here's the trick. You don't actually see the atoms directly. Instead, you fire something much smaller at them, X-rays, and you analyze the unique, specific patterns they make when they scatter. It's kind of like learning to read an atomic fingerprint. And this right here, that is the fingerprint. This beautiful, almost alien pattern of spots might look like some secret code, but it holds all the information you need to map out the exact location of every single atom in a crystal. Today, we're going to learn how to crack that code.
Okay, so let's get into it. Decoding these atomic fingerprints all starts with this incredibly powerful technique that completely changed materials science. And that technique is called X-ray diffraction. At its heart, this is our master key. It's the whole process of using these high-energy X-rays to peek inside a material and uncover that beautiful, orderly arrangement of atoms hidden within. Think of it like this. In a crystal, atoms aren't just a random jumble. They're arranged in these perfect flat layers, or planes. Now, when an X-ray beam comes in and hits one of these planes at just the right angle, the sweet spot, the waves bounce off and add up, creating a bright spot. But if you hit it at the wrong angle, they cancel each other out, and you get nothing. The collection of all those bright spots, well, that's our diffraction pattern.
So how do we actually generate these patterns? Well, let's look at the first tool in our toolbox, the law method. Its main job is to give us a quick and dirty way to figure out how a crystal is oriented in space. The setup for this is actually beautifully simple. You take a single crystal and you hold it completely still. Then you bombard it with what we call white X-rays. That just means the beam has a whole bunch of different wavelengths all mixed together, kind of like a rainbow of X-rays. Now here's the key. Because you have so many different wavelengths hitting the crystal all at once, you're pretty much guaranteed that some of them are going to strike the atomic planes at that perfect angle for diffraction. Those successful hits then shoot off and create this unique pattern of spots on a detector. And this is the kind of result you get. It's brilliant. The spots on a Lawi photo aren't random at all. They arrange themselves into these really elegant ellipses. And here's the cool part. The symmetry of that pattern you see is a direct mirror of the internal atomic symmetry of the crystal itself. It's an amazing way to quickly check a crystal's quality and its orientation.
But the Lau method has its limits. It's great for orientation, but not so great for figuring out the crystal's actual atomic structure. For that, we need a different approach. So let's bring in our next tool, the rotating crystal method. This is what gets us the blueprint. Now, with this method, we change two very important things. First, we use what's called a monochromatic X-ray beam, which just means it has only one wavelength. And second, instead of holding the crystal still, we spin it. We rotate it at a constant speed. This little chart here just sums up the difference perfectly. The Law method, right? Lots of wavelengths, stationary crystal, and its main job is just finding orientation. The rotating crystal method uses a single wavelength, rotates the crystal, and its whole purpose is to map out that fundamental structure. So as the crystal spins, different atomic planes are brought into that perfect angle one by one, and they diffract the X-ray beam. And what's really fascinating is how the spots are organized. They don't just show up randomly. They form these really distinct horizontal lines on the film, which we call layer lines. The spacing between these layer lines is incredibly important. It basically acts like a ruler. It lets scientists directly measure the dimensions of the crystal's unit cell. And the unit cell is the basic repeating block that builds up the entire structure. This is how we get the blueprint. Okay, so both of those methods we just talked about need a single perfect crystal, which can be really hard to find or grow. So what happens when you just can't get one? Well, that's where our third and maybe most versatile tool comes in, the powder method. This setup here is pretty similar to the rotating crystal method. We're still using a single wavelength X-ray beam. But instead of a single perfect crystal, our sample is a fine powder. Yeah, basically just a pile of dust. And the absolute genius of this method is that the randomness is actually the whole point. See, a powder contains millions of tiny little crystals, all pointing in every possible direction you can imagine. This means that for any given set of atomic planes, you're guaranteed to have some crystals that are perfectly lined up to diffract the X-rays. These diffracted beams then form cones, which show up as these perfect concentric circles on the film. And this quote from the source really nails why it's so important. For tons of real-world materials, we're talking metals, ceramics, minerals, things that just don't form big, pretty crystals, the powder method is the only way to figure out their atomic structure. It is the indispensable workhorse of materials science.
So, there you have it. With these 3 tools in our kit, the Lao, the rotating crystal, and the powder methods, we have everything we need to uncover the secrets hidden deep inside matter. In the end, it all comes down to this. Scientists take these patterns, the spots, the lines, the rings, and by carefully measuring their exact positions and how bright they are, they can work backwards. They use some pretty powerful math to translate that 2D fingerprint into a full 3-dimensional map showing where every single atom is located. And look, this isn't just some abstract academic exercise. Understanding these atomic structures lets us design stronger, lighter metals for airplanes and spacecraft. It lets us see the exact shape of proteins so we can develop life-saving drugs. It's the absolute foundation for creating the next generation of batteries and computer chips. It is fundamental to pretty much all of modern science and technology. So we've basically learned to read nature's most fundamental language. We have the instruction manual for how everything is built, atom by atom. The only question left is, with this incredible power, what amazing new things are we going to choose to build?